Let's start the example creation. So first we will go to the Simulink block and then we will select the blank model. In the blank model we will go to the model settings. Here we are going to select the appropriate hardware. We go to the hardware implementation. In hardware board we select our launchpad TI Delfino F28379D launchpad. We wait for the settings to load. Then we select Simulink or embedded coder hardware support package. Now as we can see, our controller is correctly selected. We now click apply and then OK. Next we are going to create the hardware interrupt. So the hardware interrupt we will configure is for the third channel of ADC1. We will use the hardware interrupt block, and the hardware interrupt block is present for C28X. So you can because C28X is our current processor, so we select C28X hardware interrupt. We double click this C28X hardware interrupt. We configure now the CPU interrupt and PI interrupt number. This will configure the interrupt for ADC1 channel 3. The Simulink task priority we can set it to a value between 0 to 30, and last value can be 0 or 1. It doesn't really matter for this example. Now we are going to make a subsystem for our control block. As we are going to make this subsystem as triggerable system, so it can be triggered by the hardware interrupt. We will use the trigger function to make it triggered by the hardware interrupt. We will configure it to the function call. Click apply, OK. Then we go back and we link this subsystem trigger to the hardware interrupt. So this subsystem will only run when the hardware interrupt occurs. So our control loop will also run in the hardware interrupt, not in any polling loop. Now that we have configured the control system, we will start placing our modules inside this control system. We will start by placing the measurement module. For creating the measurement module, we will start by a subsystem and naming it a measurement subsystem. We go inside this subsystem. We are using ADC blocks for getting the data from the analog channels. We have 6 analog channels, so we will be placing 6 ADC blocks. We will select the appropriate ADC from here. The first 3 channels in the ADC block are for the phase currents. The second the fourth and fifth channel will be for the phase voltage. The fourth channel will be for the VDC, and the fifth and sixth channel will be for phase voltages. So next we will see the configuration for these ADCs. First is the module. We have ABCD modules. Then there's a resolution. The resolution is 12 bit. Then we are SCC. the SOC we will select 1, then we will have the acquisition window set it to 300. As we are triggering it through a PWM, we will select the SOC trigger through a PWM1 SOCA. After that, as we have the sample time configured through an asynchronous event, so we will set it to -1. Because we want the output data type to be configured automatically, we will set it to double. Then we click apply and then OK. Before as we are using the channel 1 is for an analog in 0, so we make sure that input channel is ADC in 0. Now that we have configured the first ADC channel, we will replicate it with ADC1. This will be the second channel. Then we will configure the settings. The module will be the same. The SOC should be different for each conversion for the same module. The input channel, we have ADC in 1 for this channel. We click apply and then OK. After that, we have A in 2. We will configure it for ADC in 2. The ADC module is the same. It's ADC module A. The SOC trigger should be different, so it should be SOC3. The SOC3 will be the last SOC that will be working, because we have SOC 1, 2, 3 for ADC module, so the last conversion will be for SOC3. So the interrupt that we have configured is also for ADC A channel 3. So this channel we has to configure for the end of conversion trigger. So we will set the interrupt for end of conversion for this channel. So the first interrupt we are triggering for this ADC int 1. Continuous trigger is not required, so it's apply and then OK. So we have configured the 3 ADC channels. The fourth ADC channel we will configure the fourth ADC channel from A in 0. The ADC module for this is B, and the input channel is channel number 0, no, channel number 4. So resolution will be the same, the SOC trigger, and we don't need to change anything else. It's apply and OK. Then we set the B in 5. The channel for this is ADC in 5. The last channel will be for ADC module C, and the conversion will be for ADC into apply. OK. So we have now configured all the ADC channels. After we have acquired the values from the ADCs, we will now scale these values, because the ADC values from the analog ADC from the ADC will be a digital code, so we will have to convert according to the ADC resolution, which is 12-bit. So the 12-bit for the 12-bit resolution, we will have the value 2 power 12 as a divider. So we will have, because the value is always positive, so we will have a bias of half the value of 2 power 12. So the bias is 4096 divided by 2. It's negative, so that the value is between 2048 to minus 2048. The gain will be also, because we are the current sensor is 20 ampere range, so its value is from -20 to 20 ampere, so the total range is 40. So the gain will be 40 divided by 4096. Now we click apply. So this will be the gain for all the current sensors. We connected to the ADC block. Now we replicate this for all the current channels. So all the current channels have the same scaling factor. So after that we have the voltage channels. So the bias will be the same for the voltage channel because the codes are same. It's a 12-bit resolution, but because the range of the voltage sensor is different, it's from minus 1000 to 1000, so it should be 2000 divided by 4096. So the other three channels are voltage channels, so these will be the same. So this is the scaling factor that we have applied for each channel. Now the output value is between the maximum and minimum range of the sensor. As the ADCs are generally operating on the basis of op-amps, so we have some bias on each analog measurement. So we have assessed this bias. So we will subtract this bias from each channel. These biases are already pre-computed, so you will have to insert these as it is in each block. For different channel, for each channel it will be a little different. We add this block to each channel. So we have configured all the biases correctly. Now we will put our output marks for combining the current and voltages. This is for the current, so all currents will be outputted with a single port. We will name this output port IABC. These are the phase currents. Now we have the VDC. This is a single measurement. Next we will have another mux for the voltage measurements. We have two measurements, but we will have third measurement computation for the balance load. We will name it VABC. We will create the third channel or the C phase from A and B. So we set both to minus. This equation is for the balance module, balance load. We subtract A and B phases and we get the C phase. This is the measurement for VABC now. So this in short is our whole measurement block, which contains scaling and other stuff. Now we go outside this measurement block. It is completed now. We will place go-to blocks for tagging these measurements. We connect these go to blocks to the appropriate port. We have completed now the measurement section. Now we will move on to the next section, which is the basic core block of our power system. So this control block will be responsible for computing the duty cycles for all the switches. We create a subsystem, we name it the control system. We go inside this control system and delete the pre-configured. The first block we will be building will be for the reference current. So we want to get the reference current from the ABC voltages. So we set the input reference voltage and reference VABC. Now we have to implement a PLL. This PLL block, this is a sinusoidal PLL block. This is for three-phase PLL computation. Uh, we can select this PLL block by inputting sinusoidal, then sinusoidal measurement PLL. So this takes the input three-phase voltage, and then it outputs the frequency, angle and magnitude of the three-phase. So we don't need now the frequency and angle, we only need the magnitude. So we will terminate the frequency and angle. Now the magnitude block is constantly changing, so we will apply a low pass filter. This low pass filter will make the output for a little stable for the PI controller. So we set the gain and time constant. These are arbitrary values. We can set it according to the system. Set apply and then OK. We connect it to the magnitude block. Now we want to compare with the reference voltage, so we will get the error from subtracting Vref from this, subtracting this value from Vref. This is our error now. So we subtract Vref minus, so Vref minus the magnitude. This is now our error. From this error we will compute the reference current via PI controller. So we set a PI controller. So because we are working on a discrete system, we will have a discrete PID controller. So we correct the error, then we select discrete. After that we have set arbitrary, proportional and integral values. Now we have PI controller. No, we don't need a PID controller, so we remove D. we initialize the integrator from 0, and we have to saturate the output from 10 to minus ampere. We don't want the output to be greater than minus 10 ampere for this PID controller. The reference current should be between 10 to minus 10. So anti-wind up will limit the saturation, so when the saturation is at 10, it will clamp it at 10. It will not increase the integral value. Please apply and then OK. So after this we have now the reference current value. So we will make a go-to block for this reference current. We name it ID ref, and we connect it to the output of PI. Now that we have the value of the ID reference, we need the angle for the current so that we can generate the output current sinusoidal waveform. So for the sinusoidal current waveform, we need the fundamental frequency for the output sinusoid, and we also need the step size or the step frequency that will be the same as the control lobe frequency. So we take two inputs in this block, frequency and PWM frequency, or the control frequency. Because we need the radial frequency for this, we will use or multiply this frequency with 2 pi for getting the value in radial frequency, radians per second. For this we will introduce a gain block. We will set the gain to 2 pi. Then we divide this by the PWM or control frequency. This is now our step size. Now this is our step size that we have to increment the theta after each step of the control loop. So for now we will try to get the absolute theta. For this we will add the step size to the previous value of the theta. So we leave the previous value of theta for now as it is. We add a bias because we want to roll over this frequency, this theta should be between 0 to 2 pi. So whenever this theta is above 2 pi, we want to switch it back, subtract 2 pi, so that it is always between 0 to 2 pi. So we add a switch block. If this value is greater than 2 pi, we use the upper value. If the value of theta is above 2 pi, we set the bias to 2 pi minus 2 pi, so that it will roll back to 0. If it's not greater than 2 pi, then we will use the same value. Now the output is the theta. We have to use a delay block because we want to use the previous value of theta or the value of theta in the previous control loop. So we get the output omega t is I minus 1 from here. So this is the step size and this is the previous value of omega t, and here we get the omega t. So we use a go-to block and set this value to omega t. Now that we have both ID reference and omega t, we will start by implementing the current control loop. So we take the input IABC currents. Now we have to convert these ABC currents to rotatory axis. We will convert it from ABC to DQ0. The omega t that we will use for this one is the omega t that we have generated. We get a from block and use the omega t that we have generated. The dq0 is now a single vector. We will distribute it by using a mux, so we can separately process both d and q. The zero value is of no use for us, so we will use a terminator to terminate it. The D and Q axis will be will use a PI controller. So first we will use get the error for these. For the D we will get the error from ID reference. We use a subtraction block. We use another subtraction block to get the error in Q. The Q should be 0 for real power. Now we are going to apply the PI controller. The PI controller for D and Q is always same, so we will set the proportional integral for them as the same. We set the values as arbitrary. You can change it as if you require. The output saturation should be one directional, so it's going to be from 0 to 5. We replicate the same block for Q. So this is the output of our PI controller. Now we have to convert the values from DQ to alpha beta so that we can get the SVPWM. So we will output a constant 0. We will input at a input it into a demux. Now we have the DQ0. This DQ0 reference can be converted to alpha beta with the help of the omega t. We will use the DQ to a alpha beta converter. We place the inputs DQ0 and omega t. Now that we have the alpha beta coordinates, we will use the demux to separate the alpha beta components. Now we are going to introduce the space vector generator. This will generate the duty cycles for all the switches on the basis of V alpha and V beta. We don't need the 0, so we will terminate it. We again mux the output for this space vector generator to get it in a vector form. So we have the space vector PWM from this mux, but it is between 1 to -1 or the modulation index. So but we have the duty cycles for the PWM between 0 to 1, so we will scale it from -1 to 1 to 0 to 1. So first we have to apply a gain of 0.5. Then we will add a bias of 0.5 to offset it from 0 to 0.5. So this is the output duty in cycles for the inverter, and these are in the range of 0 to 1. But to make sure that we have that there's no overflow, we will limit these using a saturation block. So we will limit it between 0 to 1. We will call this as a output. This is the inverter duty cycles. Now that we have completed the core stages, the core control system, we will now move to the next phase. We will connect the inputs of the control system. We have the VA, BC, V reference frequencies, so we will get the from blocks to get the values from the measurements. We will connect VABC, IABC. The reference frequency should be a constant, so the reference value will be a constant, so we need a peak to peak reference of 110 volt, so we will connect it to the VREF. The frequency that we need is 50 hertz. We are going to design for 50 hertz, so we set to 50 hertz. Now the PWM frequency, we want to change the PWM frequency in the runtime, so we have to link it to the clock frequency of the timer so that we can control the PWM frequency within the code. So first we see the hardware settings. So the CPU clock in our configuration should be 200 megahertz. So as we can see, it is the clock in the clocking section, it is 200 megahertz, so the timer will be 100 megahertz. So now we start by including the timer clock, which is 100 megahertz. So we name it the timer frequency. Next we are going to divide this timer frequency by the PWM frequency. So this will give us the clock cycles. So this will give us the clock cycles for the timer to achieve this frequency. We will add a go to block for the timer clocks. We can name it clocks per PWM. So next we have another go to block. This will be named as the PWM underscore frequency. It will represent the PWM frequency for our control system. The timer, as we have discussed before, is working in the up down counter mode. So if we remember the image that we have seen before, the image um, shows that the uptime counter mode. So the black is the timer counter, so it first goes up to the value of period and then goes to 0. So the frequency of this signal is half of the frequency of the PWM. So we put a go to block a from block here. We use the clocks per PWM and we divide these clocks by 2, or we can multiply it with 0.5. Now this represents the clocks, the number of ticks or the number of clocks for the timer that we have configured, that we have to configure the timer module to. We can name it timer period clocks. So this area right now is for the configuration of timer and timer related ticks. So we have connected now all the inputs. So we will now connect the output to a go to block. This will be the duty cycle for the inverter. So we will name it as it is. So we will name the go to block duty cycles, or D. Now that we have got the duty cycles, we will now move on to the next step. We will generate the timer references from these duty cycle values. So if you remember in the previous image, you can it's represented by the red line. These values, we have to convert these values from 0 to 1 to the value 0 to the period. So we multiply duty cycle with the timer period clocks. This will scale this value from 0 to 1, uh, from 0 to 1 to 0 to timer period clocks. The output of this value will be muxed. So this value, we have 3 duty cycles, so we will distribute these duty cycles to 3 different modules for supplying it to 3 different legs. So for the PWM module, we will implement EPWM. We'll go to the appropriate block. For the EPWM1, we will now double click this module, which will generate the PWM. So we select the module here, EPWM1. We have the timer period units in clock cycles. So these are the clock cycle that we have converted. The timer period will be the initial timer period, so it doesn't really matter because it will change at the first period. Counter equal to 0, so the time period will always be updated in the timer period when the timer value is equal to 0. So reload of time base period when it equal to 0, because it is now up down mode, it goes from 0 to 1 time period and then 0, so we change it to counting mode up down. Now in EPWM A, this is the channel for first switch of the leg. We enable it, then we at 0 and period we change it to do nothing, because it doesn't do anything when it crosses 0 crossing. If you see the example here, it will always change when it is equal to the reference value, which is represented by compare A or compare B in this module. So it, while going up it will clear, while going down it will set to 1. Similarly in PWM1 it will be the opposite of the previous one, it will be do nothing here, and then when going up it will be set, while when going down it will be cleared. As you can see in this image, when going up it sets from 0 to 1, and when it goes down, the timer goes down, it goes from 1 to 0. So we set it to set, then clear. Then we have counter compare. So this is the compare value or the reference value. So we have to also to change this equilibrium1 because we want to get the value from input port. So we will change it to input port. Next we go back to counter compare. So we get the input counter value or the reference value from the input. So we change into input port. The input value will be updated whenever the counter equals to 0 or the reset event. So it is represented in the previous diagram also. We have the deadband unit. So because we want to introduce the deadbands, we will enable the deadband for both PWM1A and PWM1B. We set the PWM1A and PWM1B value to 220. We also want to change the data value from the model, so we will change it to input port. So we set apply, and then we go to invert event trigger because we are triggering the ADCs from PWM1. So we will enable ADC start of conversion for module A. We will enable it for the first event, and it will always update at counter equals to 0. So whenever the time reset event occurs, the next conversion will start. Then press apply and OK. So the T is the timer period, omega WA is the reference value, while RED and FED are the dead bands. So we connect this value to WA because it is the reference value. The timer period is timer period clock. We can for the deadband we have to do some computation because we want to change deadband from here. We will set the deadband to 2 microseconds from here. We will use the timer clocks to compute the appropriate number of clocks for the deadband. So for doing this we will divide this 2e power minus x, or we can multiply this with the frequency. So for the timer PWM timer frequency, we have to introduce a go-to block so that we can use it in the deadband block. So we will name it timer frequency. We use a from block from timer frequency. After multiplying these two, we have the appropriate number of dead clocks, which we will output to the timer or PWM module. These are DT clocks. We will name it DT clocks for now. We use a from block here and change this to DT clocks. We now connect these two to the DT clocks, because this will be the same when going up and down. Similarly, timer period clocks is a timer period. We will say use the same configuration twice. For the other two legs, the WA we will connect to the other two duty cycles. Now we are going to change the PWM module. Other settings will be the same. We will disable the event trigger for the other two, because these two are not starting the conversion for any ADC. We set it to EPWM3 and we disable the event also here. Now we can go through our algorithm again. So we first measure, then we have the control system, and then we output the PWMs. The whole control system is triggered through this ADC. So inside this control block is run only when the interrupt occurs at the ADC. So we go to the control system now. Now we want to control these PWMs. So if we want to disable or enable these PWMs, we want to add a manual control in this model. So for this purpose we will include a constant block. If its value is 1, the model will be enabled, otherwise it will be disabled. So because the polarity for the PWM 1 2 3 is inverted, so we will introduce a NOT gate. uh, After that we have the inverter enable signal. We will go to add a gate go to block and name it inverter enable. We will then connect this signal to all the PWM modules. So for doing this or adding this functionality, we'll go to the PWM block. If value is 0, it will be disabled. We will go to the PWM block. Now in the PWM block we have a trip zone unit. So you can see a trip zone unit here. We set this to input port. So when we set this input port, we get another input at the PWM1. Apply and then OK. We add the trip zone unit input to the other two modules, second module, and for the third module we do the same. So whenever there is a 1 at TZ select, the output of the PWM will be disabled. So that's why we have added a NOT gate. We connect it to the inverter enable signal. We do the same for the other two PWMs. So if you put 0 here, this will be disabled. If you want put 1 here, all the PWM channels will be enabled. Now that we have created the inner loop, we will try disabling the control system in case if there is any hard fault. So even if we have enabled by software, it will still protect the system. So we will add a subsystem. We go inside the subsystem now. This is for the fault protection. We will add all input fault monitoring here. So what we have to do is we have to add a digital input block. So we get a digital input for F2837XD. So the first input, so we have SCP, OCP, OVP, SCP and OTP. So first we will configure the OCPs. It's GPIO 122. You can set the sample time as you prefer, but make sure that it is not too large. So there are 3 OCPs for each leg. So for each leg there will be 1 OCP, so in total there will be 3 OCPs. We will set it for the second leg, then we will set it for the third leg also. Now we have to put a OR gate. We have configured it to boolean so that we can OR these. We have 3 inputs, so if any one of this is 1, it means that we have an OCP overcurrent. So overcurrent protection is on, so we should disable the PWMs. So we connect our output here, which will be the named the OCP. So similarly we have 3 OVPs, so we can use the same block here. We will name it OVP. Now we have to change the GPIO numbers for these, so it should be GPIO number GPIO number 124, GPIO 125, and GPIO 95. So we have configured the OCP and OVPs now. Now we have to configure the short circuit protection and the over temperature protections. We have one one input for both of these, so we will only copy one of this. First we have used the SCP, so this is the SCP. Now we will configure the same block for the OTP. We name it accordingly. So this is our protection block. So we have all these monitorings for we can monitor the faults here. So after we have these faults, these are all in Boolean format, so we can add a gate here. We can add a OR gate, and we can add a OR gate. So if any of these is on, we have to disable the PWM. So we have a disable signal also. So we have 4 inputs, so we connect these. So if any of these inputs are on, we have a fault. In case of fault, we need to disable the PWM. So we have a digital output. If we give 1 to this, output, the output signals will be disabled, and all switches will be forced to 0. So we connect output of this to this output and configure this for the disable signal. This will disable all the gate signals.